If we are given a function f of x and then its graph is shifted, stretched and or mirrored, then we know that the equation belonging to the new graph g can be written, g of x can be written in this form. So f of x minus u divided by k, the whole thing times c and plus v. And this means that c and k are stretching factors, k the stretching factor at the y-axis, so in this direction, here the y-axis, we stretch in this direction. The c is the stretching factor at the x-axis, here the x-axis, we stretch in this or this direction. And uv is the shifting vector, so we shift the whole thing by u to the right and v units up. A negative stretching factor means that the graph has additionally been mirrored at the corresponding axis. And it is always stretching before shifting. If it is in the same direction, this is relevant. By the generalized exponential functions, we mean any function that is obtained from an exponential function by shifting, stretching, and or mirroring it. So we have this function f of x is b of x, b to the power of x. And since it is now shifted, stretched, and or mirrored, the new function belonging to the new graph, g of x, can be written as c times b to the power of x minus u divided by k plus v. We will show now that a simpler formula than this covers all these generalized exponential functions, namely the formula a times b to the power of x plus v. So all that I have done is I have replaced the c by the a here, so we get a times b to the power of x as we know it from before, and the plus v is still here. I have additionally used now f of x instead of g of x, just because it's more common to use f of x. The idea is still the same. What has disappeared is the u, which is the shifting in x direction, and also what has disappeared is the k, which is the stretching at the x-axis, at the y-axis in x direction. Why is this the case? Why does this formula cover all the possible transformations? Let us look at example 1 here, and let us rewrite now this function f of x equals 2 to the power of x minus 3 in this generalized form here. Well, we have y equals 2 to the power of x minus 3. And now think for a moment on your own how you could manage to get it into this form here. Stop the film. And here comes the solution. Well, we take that apart as 2 to the power of x times 2 to the power of minus 3. And 2 to the power of minus 3 is 1/8. So I write that in front, and I get 1/8 times 2 to the power of x, which means my b here is 2, I have the a 1/8 and v plus 0. So I've got it into this form. So I've changed from this 2 to the power of x, the minus 3 here, I've changed it into that shape. Let's look at it now in more general way. So when I have now the function b to the power of x minus u, let us rewrite that in this way. Try it on your own, stop the film, and here comes the solution. So y is b to the power of x minus u. Doing the same thing like before, I get b to the power of x times b to the power of minus u. So I have 1 divided by b to the power of u times b to the power of x. Well, b and u are numbers, so I replace that just by a, and I get a times b to the power of x. So this means that instead of subtracting some value u here from the x, I can multiply the whole b to the power of x with another value a, and this is value a is actually 1 divided by b to the power of u. Next example, let's look at f of x being n to the power of x half, and let's rewrite it again in this form here. Try it on your own, stop the film, and here comes the solution. We have y equals 9 to the power of x half. Well, we can write that as 9 to the power of 1/2 times x, which means we have 9 to the power of 1/2 to the power of x. So we have actually 3 to the power of x. So what has happened? I have just changed the base here, and I have it now in this form, namely the a is 1 and v is still 0. In example 4, let us look at the similar to example 3, just more generalized. So we have some function f of x with some b star to the power of x divided by k. And again, try to rewrite it, that we get it in this form. Stop the film, and here comes the result. Y is the b star to the power of x divided by k. We can rewrite that as b star to the power of 1 divided by k times x. And then we can write that as b star to the power of 1 divided by k and the whole thing to the power of x. And then what we do is we just replace b star by the power of 1 divided by k by another b. And we get in the end just b to the power of x. So we have seen so far that we can replace the u, the b to the power of x minus u here, by this a, which means that shifting the exponential functions by u units in x direction corresponds to stretching it at the x-axis by some factor a. Actually, the a, as we have seen, is then just 1 divided by b to the power of u, but that's not so important. When we look at this x divided by k, so when we can replace this dividing by k, which means stretching at the y-axis, this corresponds to switching the base of our exponential function from b star to some b. And we have actually seen that the new value of the base is then just b to the power of 1 divided by k. Again, this is not so important. It's more important just to understand that the one transformation can be compensated by another, or can be done by another. Let us now look at an example where all these original transformation parameters occur, and let's transform it now into this simpler form. Try that on your own, stop the film, and here comes the solution. So we copy here the function equation, and then we rewrite that as 1/2 times x minus 1. And then we can rewrite this expression now as 9 to the power of 1/2 to the power of x minus 1. This is just 3. And we split here the 3 to the power of x minus 1 as 3 to the power of x times 3 minus 1. Well, 3 minus 1 is 1/3. And we take that in front here. So we get 5/3 times 3 to the power of x plus 7. And we are in the form a times b to the power of x plus v. Here we have a, b is 3, and v is 7. Let's now do the same thing for the general form. So we have some function c to the power c times b star to the power of x minus u divided by k plus v, and let's show that we can write that now in this form. Try it on your own, stop the film, and here comes the solution. The principle is exactly the same as in example 5. So we start with the function, then first we factor out the divided by k as 1 divided by k. We get this expression to the power of x minus u, and then I replace this here by b, so that's the 1 here. And next thing, get the minus u, factor it out here as having times b to the power of minus u. B to the power of minus u is 1 divided by b to the power of u. I can take that as a factor here in front. I get c divided by b to the power of u. And what I do now is I replace this c to the power of u by a here. And I get our general transformation formula for exponential functions, a times b to the power of x plus v. So we have found that we can obtain the graph of any generalized exponential function just by taking the appropriate basic exponential function and then stretching it at the x-axis and shifting it in y direction. Forgetting about the v here, we get y equals a times b to the power of x, and this means there are 4 basic different shapes, possible shapes for the generalized exponential function, which depend on whether a is positive or negative, and whether b is larger than 1, or whether it is between 0 and 1. So think about what these 4 shapes are, try to solve it by your own, and here comes the solution. This is the shape if b is larger than 1 and a is larger than 0. Maybe you want to retry now for the other 3. Here are the solutions. These are the 3 other shapes. Here, if the a is positive, the base is between 0 and 1. We have seen it looks like this. And now if the a, this factor here in front, is negative, we just mirror the graph at the x-axis and we get this shape. And if we mirror this one, we get this shape. And if there is additionally this plus v, this means just that the whole graph is shifted in y direction by v units. We can use that now to find out how to sketch any exponential function given in this generalized form. Well, stretching, mirroring, and shifting, what does have an effect on an asymptote? We know that the exponential function has one asymptote, namely the x-axis. Stretching and mirroring has no effect on the asymptote, but shifting has. This horizontal asymptote, the x-axis, y equals 0, is shifted by v units into y direction. So the new asymptote is then just y equals v. Then we can mark the y-intercept and read off its y-coordinate, because we know the y-intercept has the coordinate 0 and a plus v. Just insert the 0 for the x here, so we get here 1, so we get a plus v. We may also mark more points if you like, for example, those with the x-coordinates 1 and minus 1. And then it makes sense to determine also the basic shape of the graph, depending on whether b is larger than 1 and a is larger than 0, so which of these 4 shapes we have, if this corresponds with all the other information. So let's try that for the example 7. Proceed as mentioned here. Try it on your own, and here comes the solution. The shifting parameter v is 3, so we find that the horizontal asymptote y equals 3. For the y-intercept, we find 0, 2.5. Well, just insert for x 0 here. So we get this, which 4 to the power of 0 is 1, and we get 2.5. Additionally, we may also look at the point with the coordinate 1, x-coordinate 1, and we get the function value 1 here. Additionally, if we like, we could also look at the point with x-coordinate minus 1, and we get minus 1, 2.875. Now let us also determine the shape of the graph. The b, the base of the exponential function, is larger than 1, and the a, this factor here in front, is negative. So if it was positive, it would look like this. Now we have to mirror it, so it will look something like this. So we have this shape. So let's draw all the points and things that we found. So we have the asymptote here that we know already. Then we know the y-intercept, which is at 0, 2.5. And we have the points 1, 1 and -1, 2.875, something like this. So when I draw now the graph, it looks something like this, and this really fits also with what we found here. Obviously, we would not need these 2 points, for example. It would be enough to have the the horizontal asymptote here and the y-intercept, and knowing the shape, we could have sketched that as well. Now let's look at the opposite. We're given the exponential function by its graph and we want to find its equation. So we use the ansatz y equals a times b to the power of x plus v. We have 2 possibilities. We can use just a general approach for any function, which means we can set up an equation system by choosing just as many points as there are, choosing as many points on the graph as there are parameters in the ansatz. So here we have a, b, and v, so 3 parameters, and then we just insert the coordinates of these 3 points into the ansatz, and we get 3 equations. So we have a 3 by 3 system, so we can solve it to find the parameters. The second way is just to use a specific approach for exponential functions. For that, first we read off the equation of the asymptote, the horizontal asymptote. In that way we get directly v. Then we can read off the y-intercept, yi, which is just a times b to the power of 0 plus v, so a plus v, as we said before, which means we can find now a simply as the y-intercept, yi minus v, which we found in step 1. And then we can use the coordinates of any other point lying on the graph to find then the last remaining parameter b. Let's do that using the example 8. We're given the graph of this exponential function. We see here we're given the asymptote. We're given additionally a few points here. Let us start with the general approach, for which we need 3 points. We're given 4 points. We'll use this point, this one, and this one, just because they have nicer numbers than this one, but we could choose any 3 of these 4 points. So we have to insert now these into the ansatz. The ansatz is y equals ax plus b, a times b to the power of x plus v. So since the point 0, 1.5 is lying on the graph, we get 1.5 equals a times b to the power of 0 plus v. And then we have also the point 1, 0 is lying on the graph, and the point 2, -3 is lying on the graph. You can fill that in by your own. Here comes the result. So we get this equation system here. Let us rewrite this, simplifying the single expressions. So we get this equation system here. And now, using the first equation, we can solve that for v. So we get v is 1.5 minus a. Let's call this 1 star, and let's use it now for the second equation. So we get 0 equals ab plus 1.5 minus a. Let's solve that for ab. So I have to do plus a minus 1.5. I get a minus 1.5 equals ab. And now I divide by a and I switch the 2 sides. I get b equals a minus 1.5 divided by a. Let us call this 2 star here, and now we insert the 1 star and the 2 star here into the third equation. Sorry, this one here. And we get this expression here. Now let's expand here the squared and subtract the minus 1.5 here. We get this equation. Now we can cancel out here this a and the a squared here, and we multiply now both sides by a. And at the same time, we expand this expression using the binomial formula. So we get this equation here. The a squared cancel out here. We add then the 3a to have all the a on one side. And we get minus 1.5a equals 1.5 squared. So we have to divide by minus 1.5, and we get as the final result a equals minus 5 or 1.5 or minus 3/2. So this means we can now find the b by inserting that into the equation 2 star here, and we get this expression which simplifies to 3, and then we insert also that into 1 star here, and we find that v is equal to 3. So we find finally that the equation of our exponential function is minus 3/2 the a times the b2 to the power of x plus the v plus 3. Now let's look at the specific approach. We can read off the equation of the horizontal asymptote. It's y equals 3, so we know v is 3. Then we look at the y-intercept, which is just 0, 1.5. And again, we know that 1.5 is the a times b to the power of 0, so times 1, so nothing, plus v. V is 3, so we find a is minus 1.5. And now we can just use one additional point. Let us use the point 0, 1 up here, 1, 0. That's probably the simplest one. So 1, 0 is lying on the graph. So we know 0 equals to a. A is minus 1.5 times b to the power of x. X is 1 plus v, that is 3. So when we do minus 3, we get minus 3 equals minus 1.5b. We have to divide by minus 1.5, and we find b is 2. Putting this all together, we find now again the same result as up here. Y equals minus 3/2 times 2 to the power of x plus 3. And I think it is obvious that this is much quicker using this specific approach.